Hello everyone. Welcome to Chapter 8, Acids and Bases. Hopefully this chapter will be more familiar to you, seeing how that acids and bases are in our everyday lives, from the food we eat to the environment, as well as in industry and to our health. For example, the pH of our blood has to stay between 7.35 and 7.45, so for you nurses, you probably know that, and so that's very important. So we have to have the pH of our blood. There's different things in the body, as well as the foods we eat. All the things that are around us involve acids and bases. There's really two ways to define, actually there's three, but for you guys we're just going to cover two ways to define an acid. And according to Arrhenius' theory, he said that an acid is produced when H+ ions are produced in water. So an example of an acid would be hydrochloric acid, HCl. When it reacts, or when it's put in water, it's going to dissociate into H+ plus Cl-. So the chloride ion as well. So basically, an acid is H+, or the hydrogen ion is the definition of an acid. Acids are electrolytes, going back to our previous chapter. They have a sour taste. They will turn blue litmus paper to red when it's acidic, and they will neutralize bases. When we name an acid and we have a hydrogen and a nonmetal, then we add hydro as the prefix, and we add ic, or IC, acid, to the end. So if we have HCl, we say hydrochloric instead of chlorine, hydrochloric acid. If we had HBr, we would say hydrobromic acid. Okay, when you have a when you have a hydrogen and a nonmetal. If you have a hydrogen on your acid with a polyatomic ion, so you may want to stop this and you may want to get out your polyatomic ion chart to be sure that you have it handy. This will be given to you just like it was previously. If you have a polyatomic ion that ends with ATE, such as sulfate or chlorate, then you're going to add ic acid, so IC acid to the end. But you do not add hydro to the beginning. Okay? And if you have a polyatomic ion that ends in ITE, then you change this to OUS acid at the end. Okay, so if we look at our examples here, okay, this is our chlorate and would be the polyatomic ion, and so we would change it to chloric acid. Okay, so when we add the hydrogen here, we get chloric acid. Okay, if you look on your polyatomic ion list, you have chlorite. This is the polyatomic ion and the charge for chlorite. If you have ITE, then you change it to OUS acid, so it'd be chlorous acid. But notice how we're not saying hydrochloric acid or hydrochlorous acid. Okay, you're just saying chloric acid. Okay, if you have a nonmetal and a hydrogen, you add hydro and ic acid to the end. If you have a polyatomic ion bonded to the hydrogen, then we add IC acid, or ic acid, if the polyatomic ion is a chlorate or has ATE. If your polyatomic ion ends in ITE, then we add OUS acid to the end with no hydro in the front, in the prefix. So here's a table of some of the acids that we've gone through. But it tells you over here the name of the anion. So these polyatomic ions you would be given in a chart. And so if we have just a hydrogen bonded to a non-metal, we would say hydrochloric acid or hydrobromic acid. If we have a polyatomic ion, then we have to look at the suffix or the ending of our name for the anion. So if it's ATE, then we add ic acid to the end, and if it's ITE, then we add OUS acid. So this one here would be nitrous acid, and the top one HNO3 would be nitric acid. So very small details, but change, which acid that you were referring to. Okay, so try to name these. You can pause and then pick back up. We have a hydrogen bonded to a nonmetal, so we're going to have to use hydro and bromic acid. That's our ending. So C, hydrobromic acid. Okay. For our number 2 here, okay, we have a polyatomic ion, which is going to be carbonate. So if we look back at let's see if we have it in this chart. Okay, so here's our polyatomic ions. We have to recognize that it's carbonate. So you look at your list and you see ATE. So if we ended ATE, then we're going to end in ic acid. So if we end in ATE, we end in IC or ic acid. So it would be carbonic acid. Okay, and you see that also in the chart here. So carbonate turns to ic acid. We have a carbon here. Okay, earlier we were looking at nitrogen, and here's an example of sulfur. We were looking at chlorine earlier as well, but we have a carbon, so it's carbonic acid. This is actually present in the blood. Okay, so here's the explanation. Hydrobromic acid for number 1 and carbonic acid for number 2. The polyatomic ion ends in ATE, so it is called ic acid. Arrhenius base produces hydroxide ions in water, so the alcohol ion or OH minus. Okay, acids produce H plus or H ion. We also call this a proton. H plus is a proton. And our hydroxide is produced when there is a base, and it is produced in water. Bases are bitter, chalky. Sometimes they have a soapy feel and are slippery. They are also electrolytes, and they will neutralize acids. So sodium hydroxide is an example of a strong base, and in water, it will completely ionize or dissociate to its constituent ion. So this is also an example of a strong electrolyte, if you remember from chapter 7. So we have a sodium plus 1. Since it's in group 1, sodium has a plus 1 charge, and hydroxide is a polyatomic ion also with a negative 1 charge. But this hydroxide identifies that this is a base. Naming bases is simpler than naming acids. If it's most of the ones we're going to have you guys know are going to end in hydroxide. And so you just name the metal, and then you say name the ending as hydroxide. So sodium for NaOH is hydroxide. Potassium hydroxide. You guys have actually named this way back when we were working on naming earlier in the semester. Barium hydroxide, aluminum hydroxide. The only time it changes is when you have this polyatomic ion here. You have a transition metal here. You have iron, and we have to put its oxidation state in Roman numerals. Okay, so this 3 here actually is the 3 that's here representing the oxidation state of iron, but end in hydroxide. Okay, we're going to come back to strong acids and strong bases and so forth, but that's just kind of an introductory to acids and bases. And the second theory is what most students remember when they take from this course, because it tells us how an acid or a base is going to act in water and what's going to happen, what's going to be produced. Okay, according to, this is called the Bronsted-Lowry theory, an acid is going to donate a proton. Okay, so you want to be sure that you remember this. An acid donates a proton, and a base accepts a proton. Okay, Arrhenius' theory that we just covered told us that an acid produces H plus in water, and a base produces hydroxide in water. That's all that was told to us, and the first theory was developed years ago. And then from it came the Bronsted-Lowry theory. and it gives us a little bit more insight into what acids and bases do in solution. And so what we can do here is we're going to look at what's going on. So here we've got a proton. So we know this is an acid. Okay, it's not a specific acid, it's just an H+. So we know that's the definition of an acid. It tells us that an acid donates a proton. So what's happening here is it's going to donate a proton to water. Okay, we're going to look at water. Water can actually act as an acid or a base, but in this situation it's acting as a base, okay, because it's accepting a proton. Okay, so once this acid donates the proton, it's going to form a bond. Okay, so we can imagine that this is this hydrogen here. Okay, and the proton has a positive charge. And so what happens is it's going to form, it's going to accept this proton, and it gives it a positive charge because the water was neutral. Okay, if we look at it here, it's neutral. But it gains a proton which has a positive charge. So it's going from neutral to positive. So you also see it written like this. Okay, this is our Lewis structure here that we learned how to draw. But you also see it written as H3O+. This is also known as hydronium ion. So it's basically a protonated water. It's got an extra proton. Okay, this is an example of a Bronsted-Lowry base. Okay, one thing to remember, and I've written here, we've looked at some bases earlier. We looked at sodium hydroxide, all these bases that ended in hydroxide, sodium hydroxide, potassium hydroxide, and so on. Another base, and really the only weak base that we cover in our general chemistry courses, is your amine, okay, A-M-I-N-E, containing compounds or nitrogen-containing compounds, and this is an example would be ammonia. This is ammonia here. And there's our Lewis structure. These are weak bases. So if you see a nitrogen-containing compound that looks like ammonia, another example, so if we replace those hydrogens, it could look something like this. This is actually known as methylamine. But these are weak bases, and there's not that many weak bases because what happens is the weaker the base gets, they become acidic, and so we consider them weak acids. Okay, and so this is just an example of a weak base. Okay, so we're going to label. We've got a base here. Okay, so this time the water is going to act as the acid. Okay, water can act as a base or as an acid. And so an acid donates a proton. So it's going to donate an H+. Okay, so it's going to be losing one. So it's going to donate and form a bond. So we're actually forming a bond here. And it's going to put 4 hydrogens around the nitrogen. And it is neutral in the reactant side, but it's gaining an H+. And so it's going to have a positive charge. Okay, the water is losing a proton. Okay, so it's losing, so to go from here to here, we're losing a proton or a protonated hydrogen. And so it's going to go from neutral to negative because it lost positive charge. And so we get hydroxide. And this is what we would expect because we know that bases produce hydroxide. That is, so we have a weak base and it produces hydroxide. And what actually we should have, we'll get to this later, but we should have an equilibrium arrow there. Okay, so just a summary of the characteristics. Arrhenius acid produces H+ in aqueous solution or in water. Bases, OH-. In a Bronsted-Lowry theory, the acid is going to donate an H+, so it's going to lose positive charge, and a base is going to accept a hydrogen, or the hydrogen ion. Acids and bases both can be electrolytes. Acids are sour, bases bitter. They turn the litmus paper red or blue. Acids red, bases blue. there are indicators that can be used to determine an acid, or actually when you're trying to neutralize an acid and a base, when you use an indicator here. We're actually not going to cover this part of the chapter, the titrations part. But in neutralization, acids neutralize bases, and bases can neutralize acids. Okay, so let's identify what's the Bronsted-Lowry acid and what's the Bronsted-Lowry base. All right, so if you look on, you're going to be given a list. I'll tell you the page number so you can look in a second. We're going to be given a list that looks like table 8.3 on page 292. Okay, so you're not going to have to memorize a whole lot of acids and bases. Okay, so this should help you. Okay, but first we can see, and we've got nitric acid. Okay, we've got a hydrogen, and then we've got the nitrate portion. And so if we were to name this would be nitric acid. Okay, this is actually a strong acid. We're going to talk about that in the next video. Okay. So in water, we know that an acid is going to donate a proton to the base. So water must be the base because the nitric acid is our acid. Okay, so it's going to donate a hydrogen to our water, and that's going to produce H3O+. So we're going to, basically this is going to gain a proton, giving it a positive charge, and then our nitric acid is going to lose a proton because acids donate protons, or hydrogen ions. So when it loses that hydrogen, it now has a negative charge, and so we're left with the nitrate. Okay, HF. This would, if we were to name this, would be a good one to name. We have a metal, I'm thinking of ionic compounds. We have a non-metal and a hydrogen. So we're going to say hydrofluoric acid. So this is our acid. Water is our base. So we're going to donate a proton. So when we do this, we're going to lose a hydrogen ion to give us a negatively charged fluoride because we lost positive charge, and our water now gains a proton and becomes hydronium. So a common trend that you're going to see is the definition of an acid is that in water it produces H+ or hydronium. These are the same thing. This is considered to be the same thing. Hydronium and H+ are both basically the definition of an acid of what it produces in water. And so we've got two acids in water, and so we know that we must produce the hydronium. Okay, let's go through and just identify some characteristics. Okay, for number one, an acid is going to have a sour taste. Bases produce hydroxide. That's their Arrhenius definition, that they produce OH- in aqueous solutions. Bases also have a chalky, kind of bitter taste versus a sour taste. Electrolytes could be an acid or a base, and how strong the acid or base is determines if it's a strong or a weak electrolyte. And then an acid, according to Arrhenius theory, produces H+. So acid, H+, this is the same thing as hydronium, and a base produces hydroxide. Okay, we can pair up our acids and bases. So in a typical acid-base reaction, there are two conjugate acid-base pairs. Okay, we've already looked at these reactions, so it's really not terribly difficult to pick this out. Okay, and so we're going to first just need to identify our acid and our base. So here it's already labeled. These are just generic terms here. Acid and base. Okay, we know that our acid donates a proton, so we lose our hydrogen ion to form this. Okay, so we're going to pair these up. So basically it's going to look, the conjugate base, so let's go ahead and say that first. This is going to be our conjugate base. And this is one pair. So this is one pair, one of our conjugate acid-base pairs. So basically the pairs look just like each other, except they're going to either have gained a proton or lost one. Okay, and since your acid loses a hydrogen, then its pair, or its conjugate base, is going to be lacking one hydrogen. So it's going to look like this here. And our base gains a proton, so it's going to look, this is going to be our conjugate acid, and it's going to have gained a hydrogen. So they look very similar, except for they're going to be different in the amount of hydrogens that they have bonded to them. Okay, so this is one pair. We have our acid. This is our conjugate base. Then we have our base with a conjugate acid. Okay, so this is what I've just shown here in a diagram, but using actual acids and bases. So if we have HF, we know this is our acid, and I know it's already written here, but I'm just going to reiterate that if we lose a hydrogen, so we lose a hydrogen ion, we're going to form the conjugate base. So acid in red and green is our conjugate base. Water acts as a base in this reaction, and it's going to gain. So it gains hydrogen ion, and so it's going to be positively charged and have one more hydrogen on it, and so this is going to be our conjugate acid. Okay, which this is an acid, right? Our H3O plus means acid, therefore this makes sense that it would be our conjugate acid. Okay, and this is just going through again, so the first conjugate acid-base pair is the HF with the F minus of the fluoride ion. And our other pair, so here's our first pair, and here is our second pair. And they're only different, they're related by a loss or a gain of a hydrogen ion. Okay, look at another reaction. We've got, this time we have a base, because remember our ammonia or any of our amine compounds that contain nitrogen are bases. So water is going to act as an acid. Okay, and this is a weak base, actually. Okay. And if it gains a hydrogen, we're going to form its conjugate acid. Okay, so our blue and this is our first pair. Our blue and the purple compounds. Our acid is going to lose a proton, so it loses hydrogen ion, becomes negatively charged, and this would be its conjugate base. So you have a base and a conjugate acid, and you have an acid and a conjugate base. Okay, if you want to pause and try to write out the conjugate bases and conjugate acids of the following, you can. We're going to go ahead and show the answers here. Okay, we're told to write the conjugate base of each of the following. So basically, the acid has a proton that's going to be donated, so it's going to lose that hydrogen. And it's going to bear a negative charge because it's losing this positive charge, so it's going to make it negative. Okay. So our Hydrobromic acid becomes Br minus, because, or bromide minus 1, because it lost a proton. Okay? And if we lose a hydrogen here, we're going to end up with one less hydrogen and a negative charge on our sulfur. And then we have our carbonic acid again here, and it's going to lose one hydrogen. So we lost, so here we had 2, now we have 1, and have a negative charge as well. Okay, so if it's neutral and it loses a positive charge, it's going to become negative. Okay, now we have bases, and we're going to write out the conjugate acid. So a base is going to gain a proton. So our polyatomic ion here is going to gain a hydrogen, and it's going to become this compound here with the hydrogen bonded to the nitrogen and 2 oxygens. Okay, and then for ammonia, it is going to gain a proton and going to become ammonium. Okay, hydroxide, if it gains a proton, so it's negatively charged. I'll go back and talk about charge here in a second. But it's negatively charged and it gains a positive charge, so basically you have a -1 and a +1 that's going to make it neutral, so it becomes water. Okay. Here in B, we have a neutral base that gains positive charge, and so it gets a positive charge. Okay. Here we start with a negative charge in A, and we gain a positive charge, so it's almost like we've got a +1 and a -1, and we end up with a neutral. So here it's neutral because we start with a negative charge, and we neutralize it with the 1 positive proton. Here we end up with a positive charge because it's neutral and it gains 1 positive charge. And then here we end up neutral in C as well because we start with a negative charge and then we neutralize with the positive proton. Okay, so let's go through and identify acid-base pairs. Okay, so take a couple minutes to look at these. Okay, so we're looking for acid-base conjugate pairs. So here we've got an acid. If it were to lose a proton, this would be its conjugate base. So if we lose a proton, so -H+, then we're going to get a negative charge because we started with neutral, so this one is an acid conjugate base pair. Okay. If we lose a proton from carbonic acid, then we should end up not with this, but with this. Okay, so it actually went ahead and lost both protons. Okay, so here, this would be, it's only different by 1 proton. So this would not be, originally would not be the acid-base pair. For HCl, you can actually look at these. These don't look anything alike. They can't differ by different atoms. Okay, so we've got oxygen here. That's not going to be involved with our HCl. So our hydrochloric acid is going to lose a proton, and it would become chloride. Okay, so our original is not an acid-base conjugate pair. Okay, this is one from the other slide. If we have here we've got our base. Okay, it's got a negative charge here. And if it gains a proton, it goes from negative to neutral. And so it's going to gain a proton and become the conjugate acid. So this one is the base conjugate acid. Okay, we learned that amines are bases, so this is a base. So it's going to accept a proton or gain a hydrogen ion, to produce ammonium. So this is very common. You'll get used to doing this one a lot and for practice and coming up with ammonium as your conjugate acid.